Hi again, everybody. Okay, this is the last video for section 2.3. I'm sorry, 12.3 in chapter 12. And we are working with the dot product. Remember, the dot product is a scalar multiplication product. So you multiply two vectors and you end up with a scalar. So here on page 12 of our class notes, here's a quick definition of the work done by a constant force F acting through a displacement D, which is the vector PQ, is the following. So work is always, I don't know if you've had physics or you've heard this before, but work is force times distance. So in layman's terms, we put it as force times distance. So what do we mean by force? So I have this outline of let's pretend this was a file cabinet. I started here. I tied a rope to it somewhere midpoint of the file cabinet. I'm pulling it and my hands are up here, so I'm pulling it along this direction even though it's sliding along the floor. So the displacement that the file cabinet actually went is however far from this point P to this point Q is, which is the length of this vector D, the vector P to Q. Now the force that's acting on it is not all of the force I'm able to put in that direction because I'm just sliding along the floor. So actually the force that's acting on it, actually pulling it along the surface of the floor, is the scalar magnitude of the projection of F onto that same vector D. So in other words, it's length of F times the cosine of the angle between F and D. Okay, so I wasn't as specific last time I talked about that angle between two vectors. We always talk about it as the acute angle between any two vectors. So not this angle. It's as if the terminal points, it's as if the initial points were together. Okay, and we look at the acute angle, not the obtuse angle. Okay, so anyways, that's force times distance. So really, what is it? It's the dot product of the vector F force with the vector D displacement, or force times distance. So for example, let's say we have wind passing over a boat's sail. It exerts a 1,000 pound magnitude force as shown here. So the magnitude of the force vector F. In other words, the length of the force vector F is 1,000 pounds. How much work did the wind perform in moving the boat forward 1 mile? Okay, we want to put the answer in foot-pounds. So here we have a sailboat. We have the wind coming in this direction, which means that the force of the wind is pushing the sail this way. Okay, but the boat is being displaced horizontally this way. So, and I'm telling you that the angle between those two is 60 degrees. So the length of the force vector was given to us is 1,000 pounds. The length distance vector, oh, there should be an arrow over that D, but that's okay. The length of the distance vector is 1 mile, but we wanted it in feet to put it in foot-pounds, so there's 5,280 feet per mile. So the length of it is 5,280 feet. So the amount of work done is the dot product of F, the vector F with the vector D, but since we don't have actually their components, we just have this information. We use the definition of the dot product, which is length of F times the length of D times the cosine of the angle between them, which in this case is 60 degrees. You get 1,000 pounds times 5,280 feet times the cosine of 60 degrees, which is 1/2. And we get 2,640,000 foot-pounds. And that finishes section 12.3.